What's going on, Algebros? This is Mr. C, and I'm going to show you how to derive the library function called the reciprocal function. Now, this function is called the reciprocal function because of how we input or how we operate on the input values of x. Any value of x that we choose to plug into the function is going to go underneath the number 1, or in other words, we're reciprocating the value of x to get the output. So let's go ahead and start with that in mind to fill out this table of values. And you'll see that this table of values includes some decimals in it. And that's really just to give us some nice outputs and give us a good idea of how the graph is going to be sketched out from these points. So let's look at -2. If we were to plug -2 into the function, we'd have to reciprocate -2. The reciprocal of -2 is -1/2. For graphing purposes, we could just say that this output is just -0.5. Alright, so 1 point on our graph right off the bat is -2, -0.5. Let's go ahead on to our coordinate plane here. We'll go to -2 and down by half a unit. Alright, so that's our first point. I forgot my software does that. Alright, hopefully this will go away at some point, but our next input value of x is -1, and the reciprocal of -1, 1 over -1 that is equal to -1. And so another point on our graph is -1, -1. Oh, looks like I lost -2, -1/2. Let me just go ahead and put that in there. Then we got -1, -1. Now if we plug in -0.5, 1 over -0.5 simplifies to -2. Okay, in other words, the reciprocal of -1/2 this time is -2. So our next point is going to be -0.5 down to -2, and there's a third point on the graph. Now here's where things get interesting. If you choose an x value of 0, you're required to do 1 over 0, which is actually undefined. So there's not going to be a point on this graph with an x coordinate of 0, because 0 creates division by 0. Alright, so now let's work with some positive x values. The reciprocal of 0.5 is 2, so it gives us another point. Go over to the right this time by 0.5 and up by 2 units. The reciprocal of 1 is 1, so another point on this graph is 1, 1. And then the reciprocal of 2, is 1/2, which has a decimal of 0.5. So another point on this graph is 2, 0.5. Let me just kind of make that bigger. Alright, so it doesn't really look like a lot of information to infer the rest of the graph, so here's where you're going to have to instill a little bit of trust in Mr. C here. Let me go ahead and show you what a sketch of this library function looks like. There's actually two pieces that are separated, which together make up the graph of the reciprocal function. The first piece is in quadrant 3. What I'm going to do is connect these 3 points, kind of a curvy fashion, and if you were to use negative values that approach an x value of 0, such as -0.25 and -0.1, so on and so forth, what you'd see is this graph sharply turning down to -infinity. And just give me a little bit here. What would happen is, if we were to go beyond these 3 points, the graph would be shooting down to -infinity, but all the while getting closer and closer to the negative part of the y-axis. Now traveling in the other direction on this piece, what we'd see, we would extend beyond that point and just kind of hover underneath the x-axis. So this part of the graph that's in quadrant 3, if you were to trace it from right to left, just kind of goes up towards the x-axis but doesn't cross or touch it. There's a symmetrical piece in quadrant 1. In particular, if you were to connect these 3 points and extend beyond it, part of this portion goes like that. Alright, and so if we extend beyond these 3 points, we get a part of the graph that is approaching the x-axis but never crossing or touching it. Tracing it in the other direction on this piece, we'd see that the graph gets close to the y-axis while shooting up to positive infinity but never crossing or touching it. So the reason why this graph is doing this is because of the value of 0. Okay, actually x equals 0 should be excluded from our domain because that gives us division by 0. I'm going to go ahead and insert a couple of things in this graph. And by the couple of things, I mean asymptotes. Let's see if I can pick a good color for that. Let's use orange. We'll see how that works. We got on one side of the y-axis, we got a part of the graph that's getting closer to it and closer, but never crossing or touching it. And on the other side of the y-axis, we have the second part of the graph that's getting close to it, but never crossing or touching it. What I'm going to do is sketch an example of a vertical asymptote, which is going to be a dashed line going along the y-axis. That right there would be an example of a vertical asymptote. One S in the word asymptote, by the way. And basically it's kind of like this imaginary line that we infer just based on the behavior of the graph near that y-axis. There's also an example of something called a horizontal asymptote. And we'll get into more of these details later on in Chapter 5, but for now, we're seeing with the piece that's in quadrant 3, if we trace it from right to left, that this is getting closer and closer to the x-axis, but assumed to never cross or touch it. While on the other side of the x-axis, looking at the second piece, if we trace this from left to right, you see that this end of the graph gets close to the x-axis, but we're assuming it never crosses or touches it. So what I'm going to do is put a dashed line along the x-axis, representing another type of asymptote. But just based on its orientation, it wouldn't be a vertical asymptote, it's actually a horizontal asymptote. Alright. Now these asymptotes actually help us with some of the details in the table. First of all, the domain is not going to be all real numbers. There's one value of x that we should never plug in, and that value of x is actually in our table. And that value of x is 0. Okay, so for the domain, we don't want to use 0. We'll say x cannot be 0. And even looking at the structure of the function, 1 over 0 doesn't work out for us. The interval notation for that would be parentheses negative infinity, comma 0, union, parentheses 0, comma infinity. All right. And if you were to look at the graph to infer this domain, looking at the piece in quadrant 1, in order for this graph to be the way it is, we'd have to be using positive x values. And for the piece in quadrant 3, in order for this graph to exist in this way, we'd have to be using negative x values. Now there's no point that we plotted using an x-coordinate of 0, therefore, based on the graph, 0 is not being used. Now for the range, it's a very similar thing. There's one y value that's not being used, and that y value is 0. So for the range, we'll say y cannot equal 0, and the interval notation looks exactly like the interval notation for the domain. All right, the only difference is the interval notation in row 2 is corresponding to the y values, since we're talking about the range. Now for whether or not this graph is even or odd, believe it or not, this graph does have origin symmetry. From a visual standpoint, if you were to take the piece that's in quadrant 1, mirror it across the y-axis and then the x-axis, it should perfectly line up, all things considered, with the part of the graph that's in quadrant 3, and vice versa. So visually, this graph has origin symmetry, which means that the function would be an odd function. Now analytically, okay, we'd have to compare the three expressions, f of x, f of negative x, and then negative f of x. Of course, f of x is just the expression 1 over x. F of negative x tells us to plug negative x into the denominator. Simplifying that gives us the fraction negative 1 over x. Negative f of x requires that we take the original function 1 over x and multiply it by negative 1, which of course you can just abandon the parentheses to get negative 1 over x, and you'll see that the expressions for f of negative x and negative f of x are exactly the same. So for this reason, from the analytical perspective, that justifies that this graph is an odd function. As for increasing or decreasing, it's kind of a shocking thing. If you were to trace your finger along, say, the part of the graph that's in quadrant 3, from left to right, you would see that you're decreasing a little bit slowly at first, and then you continue decreasing, but as you get closer to the y-axis, you decrease at a fast rate. regardless of the rate at which you're decreasing, the piece that's in quadrant 3 is representative of a decreasing graph. Tracing the part of the graph that's in quadrant 1 from left to right, you'll see that you're decreasing as well. So this graph, both parts considered, is always decreasing. Alright, so now we have to come up with the interval notation that corresponds to these two pieces that are decreasing. Alright, the interval notation, or the values of x that correspond to those pieces, are exactly the values of x from the domain. So negative infinity, comma 0, union, parentheses 0, comma infinity. Now since this graph is always decreasing, it's never increasing. Therefore, we can just say NA for increasing. And that's how we derive the reciprocal function. Of course, if you have any questions, feel free to contact me. Otherwise, thanks for watching the video, and have a great rest of your day.